everyone hear me if I speak? I'll keep talking until someone tells me otherwise. Okay, great. Okay, so this is talk about Eddy. So the basic idea is that we are sick of programming in sort of pedantic computer languages. So you have this wonderful idea that you've dreamed up. It's entirely on you to translate that idea into a language, and the language is designed pretty much for the computer. And then while you do that, the computer sort of yells at you with error messages and bugs and all sorts of things. So it's not very helpful. So the problem here is that the input we use, sure, go ahead.
When is an error message?
So the question was, when is an error message not helpful? And
I won't shout out anything else.
the best answer is undefined is not a function. Another answer is syntax error, which is getting a little less common, but still occasionally occurs. So the problem here is precise input. So we, as humans, are talking directly to a language that's been designed for a certain kind of behavior, so computers. So it's great for a compiler. It behaves deterministically all the time. If you run it, it'll do the same thing, barring asynchrony and such. It's good for debugging because, again, it's repeatable and you can sort of understand its exact behavior. But it's not so good as an input mechanism. So as you're trying to convey your ideas into a computer, we want the computer to help with that translation process, to go from sort of, if there's an obvious fix, the computer should just figure it out and give you the code. And because it's interactive, you then still get the benefits of this final deterministic syntax. So again, we want to make the computer help with the fuzzy part of programming. So accept broken input. So sort of as you type, typos, missing syntax, all this gunk. If the computer can understand what you mean, just fix it right away. If it's less certain, if there are a few possibilities, ask, because we're doing this at sort of the IDE time. So we have the chance of asking the user for help. And because we're, again, in an IDE, be fast enough that we can run it as the user types. So IDE to less than a second. So the simplest version of this idea that we sort of managed to boil it down to is fix one line of Java at a time. So originally we had this grand plan of you have this sort of fuzzy pseudocode on the left and perfect Java on the right, and you could edit either side and it'd be great. And that's just really hard to implement. It sort of breaks programmer workflow. What would you check in? So the simplest thing we've done is just, if you write one line of broken code and the rest is inside a normal Java file, we'll replace it with the right one. Sort of fixing bugs in that one line based on context. Martin will give a demo of what I mean.
All right. So we built this thing, and I'm just gonna show you what it looks like. So I built a little scaffold here, so I have something to work with. Eddy is a plugin for IntelliJ in its current instantiation, and we haven't spent time on building it for Eclipse, and you will. So everybody has to use IntelliJ, which some may like and some don't, but that's okay. So Eddy runs in here, and it's basically this little hint that pops up. So if I say, for example, you see there's a string int here, and then there's also this int parameter. So if I say n equals test, it'll tell me, oh, you actually probably meant to write this .n. You didn't mean to assign this string to an integer. And that's kind of the simplest version of this, where it's obvious what I meant in a way. So I could have. So IntelliJ would have IntelliJ does actually, just underscore that line red and just tell you, oh, there's something wrong, and it tells you, oh, incompatible types. It doesn't actually tell me what I meant to write. It just tells me what the error is, and then I have to guess. So Eddy instead will just fill in the right thing if I accept the suggestion. Sometimes it's not sure what to do, and then it'll do something else. It'll give me several options. So we'll see that in a second. And of course, there are cases where this gets more complicated. So for example, I could say list is array list Eddy, and then I just can save myself some time typing all that stuff out twice, because that's what Java likes to do. Likes to have very specific and very kind of plain language, so to speak, and you have to specify every type as often as it occurs. But it's not necessary to understand what I mean. Like every programmer will understand what I mean here. And here it's not entirely sure what I meant. I completely omitted the parents in the end, so I could have wanted to tell it like, oh, look, there's like this integer around. So maybe you wanted a specific size. And then it's sometimes, obviously, yes, I can see you're amused. Of course, some things don't make a lot of sense. Like, yeah. And we're working on that. So it's set up to be a learning system, and it hasn't learned a lot yet. So it will still come up with these things, and you see more of them. Fortunately for us, that's lower probability. So it doesn't always make mistakes, but sometimes it will make mistakes, and that's okay. The thing is that in the end, what you end up with is Java. So, in the worst case, you've lost nothing. In the best case, you've saved yourself some time, but in the worst case, it suggested something unreasonable. You're like, oh, well, that wasn't what I meant. But that's okay. Okay, and then I can obviously do, we did away with most of the, or we did away with the need for most of the syntax. So if I do something like this, they'll be like, oh, yeah, print line, there's only so many things you could mean. And this is the one that you probably meant. And again, it could be out or error, or it could be this, but probably nobody ever uses this. And this probably not even like com.sun deploy really. I mean, so these are things that are still there. They're in my environment. They're possible, but they're low probability. So you could set these different, and you probably wouldn't see them, but yeah. So, and this whole trying to make these things more sort of do away with the syntax requirements that are really, well, sometimes they're in the way and sometimes they're just unnecessary. You can take that, to constructs, obviously. And you can, type sort of pseudocode and it'll be okay. Let me add this. Actually, let me write contain, show you something else. We kind of implemented this mixfix infix notation for that kind of a Scala thing that carried over to Java. Well, half of this is written in Scala, so we ended up actually mixing things up. So we're like, okay, well, Eddy should understand this, so here it is. And most of this grammar, as it is right now, is in a way crowdsourced by us noticing, hey, you really should understand this. Why don't you understand this? So one of the main advantages, apart from syntax, is discovery. So imagine you work in a fairly large system like this one. This whole file is full of code, and so you get confused and you don't really know how to use every little function in every library that you have. But typically you know what you want to do, and typically functions are called in a way that are memorable. So what you typically forget is, okay, what's the argument order? Which file is this defined in? Which package was that in? So so for example, I know if this is the case, I probably want to log what, and it's a warning. And then it'll tell me, oh, there's some logged things, and in particular, this is the one I want. And it figured out, okay, first of all, okay, so it's in utility. It's this class utility. I didn't know if it was utilities or utility, whatever. So this filled it in for me. I had to actually give it this logger object. That's a static thing that I had around. That's great. It's not actually warn. It's level.warn. Java always makes you write the class name unless you statically import it, but IntelliJ doesn't go as far as to tell you these kind of things. And then I messed up the order of the arguments. It's a completely, but it's in reality, once I wrote log and then some string and maybe it's at the log level, it was pretty clear what I wanted to say. No programmer would have said oh, I completely don't understand what you mean. Most programmers probably would have known what I said. So we believe that a system like Eddy should do the same thing, and it should just understand you if it can. And yeah, so that's what it looks like, and we can just it tries to be a little more clever about what it understands, what it doesn't, and it will help people in the end be more productive and so they can rely on the computer to actually fill in stuff that they don't remember or don't want to bother with. You want to? Yeah, go ahead.
I have two questions, right? First one is that, as we all know, Java is not a bug anymore.
So that's a great question. So the question is, and remember your second question. So the question is, how hard is it to teach Eddy about not only the basic system libraries, but all of the libraries out there, which is one of the main advantages, of course, of the Java ecosystem, which is really large. So the answer is, Eddy, as it is right now, knows about all of the libraries that are, it has two levels of knowing about libraries. One, it knows all the symbols that are in the project. So it will not, as it currently is, suggest you, like if you write some log and log4j happens to not appear at all in your project, and is not installed on your system, which is kind of impossible, but a different library, some maybe Spring. Right? It's not even there, then Eddy will not know about it. But otherwise, it knows about it, and it'll suggest it. And there's a second level of knowing about stuff, which is to have good priors, which symbols are very likely and which symbols are not very likely. Right? So there's two ways you learn these, and the published version of Eddy is not very far down that road. But hopefully, as we get more data, that'll get better. You can learn this from input and learning what people accept as the choice they make. So Eddy is actually collecting data. You can opt out of this, but if you install it and you let us, it'll actually collect your choices you make. And we can analyze that and then feed it back and basically adjust the priors to see, for example, that one of the priors that's in there is system.error is much less common than system.out. So even though they're perfectly equivalent, it'll first suggest system.out and then system.error, right? And so for these libraries, basically the usage frequency is lower, so it'll take longer to learn these things. And what you can do to make that easier is you can look at open source code and see symbol frequencies there, and then feed that back in. And we have started the process, but none of that is published yet. So if you want to help out, go ahead. Yeah, you had another question? Okay, so the question, to repeat, given that we likely, so the question is how would we deal with weaker typed languages? And the reason is that this particular system relies fairly heavily on types. That's why it's written for Java specifically. And the AST is not so much a problem, but basically our main constraint, apart from the priors that you can learn, the main constraint is whatever you spit out has to type check. And that's a very strong constraint in Java. It's a much less strong constraint in say, JavaScript. So we are working on JavaScript, and JavaScript will have like a very different kind of backend. And we'll talk a little bit about it later. So you can see what we do for this, and it relies pretty heavily on types. For JavaScript, you will do it differently. There are approaches to do it in JavaScript. They will be a little more fuzzy and sometimes wrong. But yeah, so go ahead.
Do you use engine of your own?
So there is, in the end, what we output is standard Java. Huh? Oh, sorry. Yes, so do we use the Java standard type system, or did we build some inference on top of that? The answer is what we output is obviously has to be legal Java.
Yes.
So, however, our type inference is somewhat stronger than the one of Java, but it's a little bit tricky to say that because we actually don't necessarily assume that what the user typed is correct, is what the user meant. We always have this probabilistic process where we say, like, yeah, you typed this, you put this cast here, but you probably didn't mean it because probably you meant something slightly different. So yeah, it's a little hard to say like where the inference stops and where like just corrections start. But yeah, it's a little bit stronger than what Java provides. Okay. Okay, I'll switch back to. Oh, I totally. Some of you may have seen this, but I totally forgot my favorite line. I want to show this because I like it. And again, it's standard Java, so everybody will know this. But so let's say I want to fill this list with stuff, and I just have to say it because I really like it. So I'm originally a C++ programmer. So I always get really upset by Java's parametric method call, like type parameter in a method call syntax. You'll see what I'm talking about. So let's say I want to add some stuff to the list. And I want to add there. I have this method here. It's a parameterized method, get as array, and actually, yeah. So here you go. So this is what I would write as like a C++ program. Obviously, that's not legal. And what is legal is this wonderful expression here. Continue to add all list, and then this dot, you have to follow him with this, and then put your type parameters there. So this is correct Java, which is wonderful. I don't have to know this anymore. So from now on, I'll just assume that it's C++ and it's right, and it'll be fine, which I do quite a bit, and then it's annoying because it doesn't actually work. But now it works, so it's great. Thank you.
Thank you, Martin.
Oh, we're not done. Yeah.
We're not done. That was just the demo. So this is how it works to sort of follow up on your hypotheses. So we're plugging for IntelliJ. It's about half and half Scala and Java, which really means that all of the logic is in Scala and all of the boilerplate is in Java. The implementation is sort of most of a normal Java compiler. This is the front end part, but unlike a normal Java compiler, every piece of the compiler can say, well, it could be this or it could be this. This is more likely. Someone else decide, and that ambiguity will filter through the rest of the compiler and figure itself out. So the algorithm is we read the input, sort of parse it, and we parse it using a fairly sort of fuzzy, flexible grammar. So you could have a dozen parses that are possible. So we someone leaves out parentheses. You don't really know what they meant to write, but we're going to handle that later. So we parse it into, say, a dozen possible parses, and then for each one, it'll expand, generate this tree of what it could mean. So if it is a bunch of parts of the line, like this part could mean X, Y, and Z, this part could mean A, B, C, and we sort of explore that tree using brute force search. But while we do that, we're constantly pruning away bits that aren't valid Java or are unlikely according to the prior. So if we have two different choices, we'll pick the most likely one first, and then only go to the less likely one if we have to. And that lets us hide the sort of exponential blow up in the search space behind sort of lazy evaluation. So luckily, parsing one line of Java is easy. So IntelliJ is lovely because it does everything, all of the rest. So if you're writing a whole file, we let IntelliJ do all of the work for the rest of the file except for the one line you're currently on. And that one we can use sort of slow, cubic time dynamic programming. And then again, we use it. That's important because we want to handle ambiguity. So our parser is sort of the Java grammar simplified and extended so you can be a little more lax. So there's several different ways of applying functions. You can drop new or add it where it shouldn't be, and it'll sort of ignore it. Lots of choices like that. And that gives you sort of this large number of sort of possible parsers which we'll search through later on. And also we can sort of add in mismatched parentheses. So if you mix those up, we'll try to stick them back in for you in the most likely way we think. The way we implement this, I think there was a fun talk a couple months ago at this meetup on the Twitter people doing sort of the futures monad for how they sort of structure asynchronous compositions or asynchronous computation in the JVM from Scala. We're also doing this sort of monadic structure where we're sort of using weird control flow. So we have our whole compiler inside this scored monad, which represents sort of this lazy list of alternatives. So it's probably this, maybe it could be this, then these options are much less likely. And it's ordered so that you don't expand the sort of the tail of unlikely options until you need to. These scores are sort of viewed as like 0 and 1 probabilities. And when you if you do two things, if I say A comma B, and the score of of A is 0.7 and the score of B is, go ahead.
So is the number that it was showing next to each string, that was the...
Correct. So those are what you get when you multiply all of the scores together from all of the choices it made. So Eddy can fix multiple mistakes at the same time, but as you do that, the score gets lower and lower and will push it sort of below other more likely options. So here's an example. So for some reason, Java and also nearly every other language, like Scala and C++ and blah, 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 you can't put parentheses in types, which is confusing because they can go everywhere else. So we allow that, but because it's not valid Java, we assume that it's less likely you're going to do that. So if we see some parentheses around a type, we'll say, well, that's fine, but we're going to reduce the score by a factor of 0.8, and because this is lazy, we'll only evaluate it as a type if that 0.8 isn't enough to make it unlikely. So if someone else says, oh, I can beat 0.8, I can beat 0.9, we'll completely ignore this sort of type expansion and then sort of save effort. And again, what this lets us do is sort of keep flexibility. So we do allow parentheses and types, but we don't allow them as much as we allow something else. We have this sort of fuzzy notion of what things are legal. So because we have a monad, there's these various ways of combining different sort of compiler computations together. So if you have one value that you know, that's sort of a singleton list. If you have one computation, say a list of function arguments, and once you've computed that, you can compute a function call, then that's like flat map. If you use sort of monadic structure that you've seen this for Scala. If you have two different computations, like you say f of x comma y, and there's sort of two different lists for x and y, those can combine as sort of a Cartesian product. And again, this biased one is just a simple case of one thing but less likely. So here's an example to make this a little more concrete. So say someone types print line x. So this is almost valid Java. It's almost the thing on the left, which is declaring a variable of type print line with name x. But no one would think it means that, actually. So, but because this looks closer to Java, we'll first do the thing on the left. So we go over here and we say, well, let's see if print line is a type. So we look it up in our environment, and so we first check if it's in scope. No. We check if it's sort of a variable that's nearby but not quite in scope. No, print line is not a type. And then maybe it's a typo. Maybe it's it's print line with a capital P. But because this bias has reduced the score to 0.5, we're going to stop there and go over to the other side where maybe print line is a function call. So we've left out the parentheses, so we'll bias that by 0.8, which is better than 0.5, so we'll do that next. So is print line a callable? Well, there's a couple things it could be. It's not in scope. Could be this weird static function, which is possible but unlikely because no one wants to call really long static functions which aren't imported. So maybe it's a non-static thing. So we do this sort of a flat map operation to find variables which might be objects that you can call print line on. And sure enough, we find one. And it's really great. The prior says there's no penalty for using system.out. Good choice. So the result is we've sort of interpreted this line of code, which looks more like a variable declaration to Java, into the thing that every programmer would assume that it means. It's obviously a call to print x. So the fun thing about this is that then if you've sort of set up this monad and these various ways of handling ambiguity, the optimizations are about knowing what you need to know when and sort of pushing as much laziness as you can. So the expensive sort of exponential blowup, which we have, happens later or not at all. So for example, if you have two computations that are totally independent, they're two separate lists, then that's a faster structure than if the second list depends on the first list. Because then you can evaluate each one independently and then combine them, as opposed to doing sort of in sequential sort of blow-up fashion. I'll skip the next option. If anyone happens to do Haskell, this is sort of the same analog as applicative versus monad. So sometimes these weaker monad structures give you faster code. So most of the compiler logic is written in Scala. And Scala is wonderful, but it's very slow. So we have to make it faster. So we have this lovely functional sort of weird functional programming abstraction called the ScoreMonad, nearly all of which is written in Java, because Java is imperative, it's fast. It's really nice for writing sort of bare metal, which means JVM constructs. So the ScoreMonad is written in sort of highly optimized Java, but it looks functional to the outside, so our compiler can behave as if it's working in this sort of purely functional environment. Scala also loves to allocate memory, which is terrible on the JVM. If you do it as fast as sort of we end up doing. So the Java implementation of the ScoreMonad tries to skip as many allocations as it can. And what that amounts to, sort of intuitively, is if you start looking inside a computation, you want to look as far as you can before moving out to somewhere else. Because whenever you do a context switch, you have to allocate some memory to sort of preserve your state. And this is sort of runtime strictness analysis. So knowing how much you can do, how much work you know you have to do now before you move on to some other sort of lazy part. So more let's see, where am I? Yeah, details. So one of the things that we allow in terms of errors is every name can be a typo. So that includes variable names, functions types, null or int, so keywords in Java. All of those we look up in this large tree which allows errors. And we sort of rank those errors based on how far you are away edit distance-wise. So this is an example of laziness. So we do a first fast computation to find sort of exact matches, so because those are more likely and they're faster. And then if those fail, we reduce the probability to sort of hide this computation and then look for typos. And then, which means that we can always look for typos, but we'll only start looking for typos if this exact search has failed. So the fun thing about monads, which is sort of any application of monads, is that you can separate some weird kind of sort of control flow logic from your actual application logic. So we have a compiler. The compiler does a bunch of stuff which looks just like a normal Java compiler front end. And you don't want to have to think about the fact that it's sort of jumping willy-nilly around the computation tree, searching for different values of these lazy lists as it's doing the compiler logic. So writing the compiler inside this monad lets us keep that separate. And we can just, one part of the code focuses on being a compiler and sort of doing Java type inference and dealing with the Java semantics and AST and so on. And the other part handles this search. The problem with this is that we're writing an interactive tool, so it's as the user types, and the performance of the whole tool depends on these scores. So you can imagine that if you increase one of the scores towards 1, it's going to be more likely that lazy search will expand that part of the tree and then waste a bunch of time in possibly a useless direction. So this is a somewhat unfortunate balance where we have to sort of adjust. We can only sort of play with these scores so much before we run into performance problems, and then have to think about those somewhat carefully, which is more of an issue going forwards. Right now, we don't have a lot of sort of learning of these numbers, and as we start to learn them, that will be more of an issue. So Java is a complicated language. It's the best language for this, probably, but it's still complicated. So it has undecidable type checking, for example, sort of generics plus object orientation, just like Scala, only a little less. So we haven't yet handled all of Java. So we don't handle sort of class declarations and field declarations. We're focused entirely on statements. Extending it to the fields is not very hard, but it's sort of more work. We do handle switch, and also inner classes, actually.
Yeah, sorry.
No lambdas, though. This slide is obsolete. So we don't handle lambdas.
Yeah, but anonymous classes we do.
We do.
Yeah.
We're getting better.
Question?
Yeah.
How about one logical line that spans several ID lines, like when you're doing something with fluent?
So the question is, what about one logical line which spans several IDE lines? This is a great question, and we do handle that. So the way we currently do it is only halfway there for the following reason. We rely on IntelliJ's tokenizer to sort of eat up a line, and then we sort of have some idea of when it stops. And this is not always correct. So when IntelliJ is correct, we'll soak in the whole line and then process it, and we'll treat it as a normal line. But IntelliJ is often confused, and if you type part of a line, it'll be like, oh, and you mean these next 3 lines as well, which is not right. So we have partial support for that, and to get further, we have to be more invasive in terms of like taking over IntelliJ's tokenizer.
In particular, the problem mostly occurs if you write mismatched parentheses, because IntelliJ considers everything until it kind of gives up or finds a matching parentheses the same statement. So it'll just like expand like until the end of the function most of the time, and then we have this garbled mess that we're like, okay, whatever, I give up. So that is the main problem, and we kind of have to.
Yeah. It's not a conceptually difficult problem, because the correct way to know is usually indentation. Like, you don't want to keep searching if the user starts to unindent back to the original level. So a fairly simple heuristic captures that, and we have not implemented it just yet. Yeah. But I like that question. It's bothered us many times. So IntelliJ is kind of a hostile war zone. So all the data structures are imperative. It's a bunch of locks and all sorts of plugins and third-party stuff competing for these locks. It's very easy to create deadlocks. We, because we want to sort of index the entire project. We want to index the whole world so we can search through it dynamically. Those indices have to be kept up to date all the time. And IntelliJ doesn't like you storing pointers into its data structures. It'll blow up. And the documentation is reasonable, but it's limited. But on the other hand, we could not have done this without IntelliJ. So we are using so much of their infrastructure. So we can deal with one line and let IntelliJ do everything else, including all of the other projects and the build system and on and on. We rely on IntelliJ for parsing and for building indices. We don't have to write an editor, and of course, people are already using it, so we don't have to convince them to switch editors, which we would never be able to do. So IntelliJ is great, despite these flaws. So the next steps for us are understanding the rest of Java. So non-statements, which are pretty easy, just a little bit more grammar work. Lambdas, which are also pretty easy. We have most of the type inference there to do lambdas. The better part, the more interesting part is this prior for which things are more or less likely is handwritten by us, by Martin and I. And that's not the right thing to do. The right thing to do is to train these numbers from all of the open source code and then other code that people have written. In particular, because that gives you what you were saying, it gives you not only a search through open source, through these big frameworks, but also which parts of the frameworks people use, and even more, if you start using one part of the framework in the first part of the line, by the end, you've unlikely to have switched frameworks. So there's sort of, over the whole line, you can get a lot of information out of scanning code. And there's a lot of code to scan, which is really great. But we haven't gotten there yet. And again, the one issue there technically, which we're going to run into, is that because we have these crazy optimizations that are based on when you can be lazy and when you cannot be lazy, is you start training the prior, that will degrade. It may also speed up, because if you have better accuracy in terms of what people never do, you don't ever need to explore that until you have nothing else to do. So maybe it could be either good or bad. We will find out. Another important step is sort of clean error reporting. And there's sort of 2 ways to do this. One is the most interesting thing to do is if you have some large line, it may be that the user sort of kind of, quote unquote, meant an error message. So that they really meant some complicated thing. And most of the line is correct, but maybe one part is right, but wrong in context. So the actual bug fix is somewhere else. And as a single line thing, we can't report that. What we can say is, look, we've fixed bugs in most of the line. We think there's something fundamentally wrong with this last part. Can you help us? And sort of combining it up the tree. So that's another area for future work. That can also make it sort of much easier and more useful to use. And then we have our long-term fancy dreams. So one, as we start to apply these machine learning techniques to understand the shape of sort of real code that's out there in the world, there's starting to be these very interesting techniques from sort of deep neural networks for doing sort of natural language processing and a lot of sort of text work and images as well on building interesting priors about the structure of some space. So learn the structure of images, learn the structure of natural language. And people are starting to apply these now to code and to sort of learn idioms and sort of usage patterns from large databases of code. And this can be directly applied both to sort of autocorrect, what we're doing now, and also to find bugs and sort of do sort of automated code review and style fixing. And then there's really fancy things like theorem proving, which I get all excited by because I'm a mathematician. One thing that's important is this is sort of teaching machines to code, but if you do only a mediocre job of teaching a machine to code, you can still get useful applications out of it. You don't need to have a human-level AI before this is useful. So this here is a relatively sort of simple rule-based system. It's already useful. And a little bit better will just keep being, you can keep sort of filtering out garbage and you can sort of widening the gap from sort of where you can sort of project pseudocode to real code as sort of people type. So it's moving more and more of the grunt work from the human to the computer. So we love feedback. This is open and open source and downloadable. And it works in Android Studio as well. So IntelliJ or clones. Yeah, that's the talk. You raise your hand first.
So you mentioned, sort of lazy tree-based search, and I'm going to show it.
So so the question is, as we're sort of descending this lazily evaluating tree, how do we know when a branch has an answer and we're done, we can show it? Is that correct?
Yeah.
So the answer is that you expand the tree until you find one that you know is the best one. So if you have two options and you have basically what we have during this search are upper bounds on the score. Or once we hit an actual answer, then we have the score. So if you've computed a bunch of options and one of them has score 0.7 and the other ones have an upper bound of 0.6, you know you don't need to expand them further. And we expand, basically we expand until we get the first option and show it. And then we keep working while that thing is on the screen until we either get too low or sort of run out or find new options. And as we find new options, we show them. So we're sort of doing that adaptively if the user stops typing, we start going to work and showing them as we sort of produce answers, basically.
And then one other question, code base?
We do. So for example, we do a little bit of that so far. So the question is, do we update our priors based on IntelliJ's indices for the current project? So an example of what we do now, we don't do a whole lot of that yet, is we currently scan all of the imports and sort of produce a few sort of summary statistics which say that if you've imported this file 10 times, it's more likely that if you forget the import, we can sort of fill in the qualification for you. So you're less likely to use a function that's brand new. So we score that lower than a function that has been imported, say, in other files a bunch of times. Yeah. So the question is, what about other editors? So Eclipse, NetBeans, and then, yeah, IDEs and editors. So there's actually a distinction there. So because we take advantage of so much of the IDE's infrastructure, it would be hard for us to port to Vim or Emacs. Sorry, I forgot the second one. But it is fairly easy for us to port to Eclipse because we've done a fair amount of work to separate the compiler logic that we've written from the logic of sort of exploring indices and sort of interfacing with the IDE. So an Eclipse port is reasonable. Because we are a compute-intensive plugin, we spent a lot of time wrangling threading bugs in IntelliJ. So most of the work doing an Eclipse port is just getting around the bugs in sort of the concurrency model, which may not be bugs in IntelliJ. Some of the bugs we had most trouble with were in the Scala plugin, and so it's a whole third-party thing which we're running at the same time and is a conflict. But we do want to port to Eclipse. We haven't started it yet. Yeah.
Did you look at the CLIP?
Say again?
Did you look at the CLIP? Is that based on any academic research?
So not really. So we, this last line is the key bit. That we, oh yeah, the question is, are we basing on academic work? And actually, I may have skipped this slide. How do I get to that slide? Okay, I just show it in here. So there is a lot of work in this area, and we sort of looked at the work and learned from it and then did something dumber. So because we want to fix so many different kinds of errors that are at the same time, a lot of these are really lovely work, but have sort of, it was unclear to us that we could do them in interactive rates. So we intentionally picked something that was sort of simpler and more flexible in certain ways and more limited in others. So we're sort of inspired by some of these, but and these slides can be up if you're curious to read through these. Some of these are pretty good papers. The one that's sort of most similar to ours is this Guevara one, which is doing pretty fancy autocomplete, not autocorrect, for Scala. So they can sort of autocomplete higher order functions with type arguments and fancy stuff. Whereas, but their model is sort of this autocomplete mode where you're extending a line which you believe is already correct. And we sort of think the right model is the human puts down some stuff, and then we think it's just kind of roughly what you mean, because you made a mistake, you're human, and we'll fix the whole thing for you all at once. So it does interact, but we've sort of had a somewhat different focus from some of the previous work.
So themes of those.
Right. So there's two parts to that. So the question is, Java 8 has introduced particular lambdas, and lambdas let you do, with reasonable cleanliness, lines which have sort of unbounded complexity. You start out with a line, and then you have a whole function call there. So the first part of that is we're actually exponential time, not cubic time. Just the parser's cubic time. So the rest of it is much worse. So that's the bad news. The good news is that cubic time is just because we were lazy. There are better parsing algorithms which are roughly linear. And the real question is sort of how many errors are you willing to fix all at once that are sort of connected together? And so when we, for example, our current stuff doesn't do lambdas, but it does do anonymous classes. And when we do those, we sort of segment the line. So we kind of take the whole body of an inner class function call and treat it as an atomic token for the purposes of doing bug fixing on the rest of the line. And so that approach extends to some of the applications of lambdas, but of course not in general. Like often you really would like the thing to fix the whole thing at once. And there is a concern that obviously for certain kinds of code, this approach does not scale. We think that it captures a fairly, usually when that happens, if you start writing a bigger and bigger lambda, it will make sense to take bits of that and treat it as a block and error fix the rest, and then you can go in and fix that. So you can sort of you can sort of zoom out one level and take bits and pieces of the line and apply what we currently have to get through like large blocks of lambdas. Because even for our code, we do have situations where we say, oh, function call of new and then inner class and then a gigantic sea of code. And we, of course, can't run even a cubic time algorithm on that line without stalling the IDE. Yep? So the question is, does previous user behavior affect later priors? It doesn't yet. we have the only server-side component we have is this opt-in sort of data collection, which is anonymized, as much as you can reasonably anonymize code, which is questionable, but it's opt-in. So we're currently collecting that data if you opt in, but we've only gotten a little ways through starting to parse it, and we have not done the work of going further than that and doing, say, as you type a project, sort of what, as you write code in a project, changing the priors, and we do parse the project, as I said, to a different question and make some statistics and then go from there. What we plan to do in future is you can sort of structure these kind of hierarchical Bayesian models where you look at all of the code on the web and you'd see that maybe there are 100 types of projects, and these different projects have different sort of symbol distributions. Some projects are very sort of Spring Boot heavy, and they use these kind of Spring Boot behaviors. And you can build up this hierarchical model where if you see a little bit of user code, you can snap into a point in that space, like, oh, this is a Spring Boot project. I'm going to use the priors from that kind of those frequency distributions. And that, I think, is the sort of the right way to approach that, and does give you a lot more power in terms of what you think is reasonable code than just sort of the first line of code that you type into a new project.
I think there may have been a slightly different angle to this, where it's like we don't do currently any kind of user per user personalization, and that's definitely possible. But going from this type of offline learning to something that's really kind of online learning, where as you select certain things, it'll update your priors interactively, that's probably a bit further away. And it's a question of trade-off, like how much additional quality of result will it give you, and the biggest chunk is definitely like the embedding, Bayesian embedding of the projects, basically, where you like from the first few lines you will be able to tell, oh, is that guy using this framework, or is this an AWT project, or
Per project is also nice because if a new programmer joins a project, they will immediately be using the priors that are according to the project style. So you'll naturally be sort of guided towards what people are already typing, which is useful for large projects. Other questions? Yep.
How did you come up with the initial factor for the biases?
Yeah.
Which is arbitrary. Yeah.
So the question is, how did we come up with these numbers for the biases? And we made them up, and then we tweaked them when we didn't like the result. So, yeah. We sort of structured the system so that we have a big gigantic list of these numbers, and we hope to be learning these from data. But right now, we just made them up.
Okay. Second question. For grammar?
A little bit. So the question is, did we take inspiration from languages which cross-compile to Java, and as we edit this, as we sort of write our grammar? I think more generally, we've taken inspiration from a lot of languages. So we have, for example, we have a bunch of stuff in there that's sort of Python-y. We have sort of Scala syntax, OCaml and Haskell as syntax, and C++ is syntax, where you sort of put when you put angle brackets on the wrong side. And then when we put it out there, we got several people asking for, I want the colons at the end of if statements from Python, and so that we added that. So we've kind of added bits and pieces of languages here and there. The disadvantage is that as we're currently writing this grammar ourselves, so we have not. You really want to move to a model where you start learning the grammar, and the challenge there is the data you'd really like to learn that grammar is what people would love to type if they had the perfect system like Eddy. And there's not a lot of code which is, oh, if you were Java, if you're typing in Java but you loved Python, what would you type? There's only correct Java code. So there's a bit of a sort of chicken and egg learning problem, which we've solved by just writing the grammar ourselves by hand.
Okay.
Yeah. We don't, although that's a good that is a good idea. Currently, we have very little, we have no state. So, and that's partially just for simplicity. So if you opt into to data collection, we just send data off into a server and it's one way, but we don't maintain any current statistics. So it's all of the, say the local knowledge is based on the project, and it's pretty hard to reliably, so for example, for indices, which is unrelated, it's easier if we can, the fact that we can just blow away our knowledge and then reconstruct it is useful. So we haven't maintained any state or didn't user reports. But that's a good idea.
Somewhat or more stylish code.
So that's a great question. The question is, if Eddy learns from all the code on the internet, which is all wonderful quality, will it learn to be a terrible programmer? And the answer to that is similar to the answer about different project styles. So what you really want to do is look at all the code on the internet and learn a topic model, which says that code breaks down into these classes. There are various different kinds of projects, and you can start agnostic as to what projects are good and bad, but then you have these topics, and some of the topics are good code, and some of them are bad code, and then there's two ways you can sort of figure out, oh, now I actually want only the good code topics. So one way is if you join a project and the project itself is good code, and you're sort of a novice programmer, then it would naturally be projected into the space of good code because the project is already there. And the second way is if you have a sort of historical data, you can sort of discover that if people write code that is in this one topic, they immediately fix it into this other topic, or the commits have a sort of a certain directionality to them across Git history. And that would again tell you that like this style of code is bad and should be avoided. So as we start getting into this sort of learning process, which we're not there yet, that's actually a very important like area to go in because that's where a lot of the value is. So it's not enough to say, the power of machine learning is that you can go beyond types and say, oh, these are both perfectly valid Java, but you never write that one.
There's a different, slightly different angle to this, which is if you are allowed to scan a particular organization's code, you will adapt to whatever that organization tends to do. And so, for example, if an organization frowns upon the use of log4j, you will not suggest that. And so, that's really where maybe, in the limit, or when you think about enterprise applications, that's maybe what people actually want to do, where they're like, oh, we have this style and we have these rules, and we'd like Eddy to understand and promote these rules. And that'll automatically happen if you kind of let Eddy work through a particular organization's code, and then what it learned from that use those things in its models.
And that's again a way to do the projection. So you could learn these topics from all the code in the world, and then assume that like good organizations are on the positive side of that scale. So if you look more like organizations code, then you sort of stripped away a bunch of the gunk from GitHub, of which there's a lot. So actually, I'm not. Go ahead. So I'll say the question. So the question is, have the folks who have installed Eddy been accepting of the this logging?
So we turned this logging into an optional thing, and we have 3 levels of logging. And the kind of the initial release default was like log everything. And we had this on Reddit, and people looked at it, and you can count the comment likes or whatever, and it's probably like a quarter of the people probably didn't really like the idea of having their code logged, like really didn't like the idea. But then again, that only tells you so much. So the problem that we're having is we don't actually have, if somebody turns off this data collection completely, we don't know they exist. We can distinguish between the people who turned off the code logging and turned off, and actually haven't analyzed the numbers, so I can't tell you. But so we know there's this amount of people, and we could know there's like 20% of people have turned off code logging.
You just made that number up, though.
I totally made that number up. That could be 80%. But we don't know how many people have turned off logging entirely, without even like
That's sort of a disadvantage
No
of
code.
being, we're deployed through the IntelliJ plugin repository.
Yeah.
So we are not, the user doesn't download Eddy from our website. They download it from someone else, and we don't really get detailed statistics.
I guess my subsequent question is like, how do you compromise?
So the question is, how, if we did more logging, we could learn a lot better. How do we anonymize that data? And the answer is that we are in a space that is extremely difficult to anonymize. So, so for example, as we start learning from code, one of the most powerful information sources about code is the names of things, like the names of functions, names of variables, classes, et cetera. And so you can't say minify the code, because then you'd lose the structure, which is actually where the human information is. So we don't really know how to anonymize that stuff. There's machine learning work where people have done really fancy theoretical techniques called differential privacy, where they can train machine learning models that can't be reverse engineered. But those models are lower quality, and they're harder to train, and I think they're bigger. So it's not clear that there are easy ways to anonymize this process.
I think the real solution to this problem is for an organization to say, okay, we buy it. We want you to like install our custom version of Eddy locally, where you can scan all our code and then work with our code and build whatever model you want, and we don't have to fear that it leaks out because it's actually on our servers. And that's cool. Like that's a perfectly valid kind of model to work with. And you can still use the open source knowledge base, but the extra knowledge that you build from that company's code cannot leak outside. So I think that's the real, like for individuals, that's obviously infeasible, but because they don't produce enough code to actually train something on. But for organizations, that's perfectly reasonable to do.
But even an individual working on proprietary code of their own proprietary code can use the open source trained model,
Right.
which will sort of mimic a lot of the structure of how they program, hopefully.
And if you remove the session information from like individual lines and sort of, is it still easy?
So yes, you can do that, and you can that's kind of the security theater approach to anonymization, but it's trivial to reconstruct. Because you can just do sort of string matching, and you'll find out that these things move together. So the only guarantee we can say there is our terms of service are if you opt in, we will not reconstruct your code and then look at it. But all we can do is say that. It's really hard to guarantee that if we were as malicious. So we're pretty upfront that I don't know how to do that on anonymization technically. Yeah. So the question is, if the user ignores our suggestion on one line, do we save that work and use it later? And we don't, and that's purely a sort of a code complexity issue. So incrementalizing our whole compiler would make it substantially faster, but we haven't structured the compiler that way, and it's a lot more. It's sort of further along the meta-programming spectrum, which is always sort of a scary place to be. As you start to write fancier and fancier code, generating code. And I don't know how to do that well without writing a compiler in a very sort of declarative way. So we have this happy medium where we're using sort of reasonably nice features of Scala to do this abstraction, to build a compiler that can do search. But to build a compiler that can do incremental search is another layer, which is just, it's a performance hit or a lot of metaprogramming. Benchmark, the question is, are there benchmarks on the size of the code base and how performant it is?
Well, we do know, so I mean, we use it for our own project, which includes all of IntelliJ. So if your project is smaller than IntelliJ, you're fine. If it is, what happens is actually that, so we use IntelliJ's indices, and they have a certain size, and IntelliJ's VM has a certain size, and it's 750 megabytes, which is kind of ludicrous. So if you have a large project, you have probably increased that value already, because we're not adding all that much on top of it. What we add on top of it is a lot of just running a lot of code in the background. So
to expand, we're very careful to, when we do build our own indices, but they're as lightweight as we can make them. So for example, instead of storing data structures like types, we just store strings, and then we expand the types on demand during the search.
Yeah. So
So-
we don't add a lot on top of IntelliJ's memory footprint. What we do though is we basically run one processor full time. So if you have a spare processor, most of us do, then that shouldn't be a problem. The memory is actually the bigger problem, because once you run out of memory, the VM just GC thrashes the whole thing and everything is terrible. And so if you run into that problem, you probably have run into that problem before, and you probably have fiddled with IntelliJ's like memory settings, and then you're probably okay. But that said, like the standard JVM GC just also kind of breaks after a few gigabytes of size and takes really long, and at some point there's a limit. But IntelliJ is a fairly large project, so that's actually, most people are probably okay.
I think, if I understand correctly, so the question is, are we using regular expressions to sort of search, speed up or optimize or detect correlations across these indices of symbols in a project? And we are not currently, and the difficulty is that if you build, there's one of the cases where we need to be fairly low linear time on the indices. So if you have a linear number of strings and they take up however many megabytes of memory, if we're at all super linear in that performance, then we will then thrash through IntelliJ's memory limits pretty fast for large projects, because we want the whole project's indices available. There is some, I think, as we get, if we push the priors further, and then we have a better notion for a small number of sort of hot symbols, which are more likely searched, then we can put more intelligence in searching those sort of hot symbols, and then do the slower sort of more sort of low memory thing for the rest. But we haven't done that yet. So the question is, what is the best part of this project? And for me, the best part is, you sort of, as you program in Java using this thing on, like I'm sort of gradually getting used to it existing, and sometimes like there's one time where I sort of forgot, and I was like, oh, I want to check if this file type is Java. Like, how do I do that? Like, what crazy enum in some package? And then I just remembered that, oh, I could just say, like, is it equal to Java? And then it just fixed it for me. So it found the Java symbol and fixes capitalization and sort of changed equals to dot equals. And so it's fun. It's sort of kind of forgetting that you have this ability to not think about stupid details. And I think if we sort of push this technology further, the hope is that you can sort of programming is a little bit more of a human process where you're not sort of mired in pedantic nonsense. And you can just sort of write down what you want and it'll figure out the details for you. So that's the long-term hope. And sometimes when it happens as a surprise, it's sort of particularly fun. Yeah, so these projects are the most similar. So I think the coolest one for anyone who does Scala and Eclipse, I believe, is this one. And there may be, I'm not sure if there's follow-on work yet. So this thing will do, I think most of especially either the current IDEs or this Gavero paper are autocomplete, which sort of to say what that means, autocomplete to us is I have part of a correct line, help me finish the line. Whereas autocorrect is I've written some stuff, project it into what I meant to write. Like I've made some mistakes. But this stuff is still pretty cool. So Gavero can, you say something like type x equals, like I think you would say question mark, or maybe you hit tab, and it will be able to fill in a complicated function call involving sort of several layers of calls through sort of higher order functions that are sort of polymorphic. And again, the goal is similar. The goal is to sort of reduce the amount of sort of library noise that you have to remember. So some of that is interesting. People are starting to add. So I think Xcode will do a little bit of this, so especially sort of little typo correction, and they're pushing that. I think they're not going far enough, and I hope that sort of this point It's like, oh, we should destroy them. Maybe Apple will think that, and they'll do a wonderful job, and it'll be great. Because I think that all IDEs should do this. Like, there's no reason that we have all this sort of wonderful technology now for sort of speech recognition, and we can detect images and sort of hallucinate things, and that should be applied to programming. Just because it sort of the computer can sit closer to the pedantic language details and also sort of understand human sort of syntactic ambiguities. So.
My understanding, both are pretty much paper forms, is it correct?
These are all papers, but Gavero et al. Is an Eclipse plugin, which I believe you can download.
Okay, and pretty much we also evolving, like we kind of.
I do not know that. They may be an abandoned paper by a grad student.
I'm very sure that sloppy programming is abandoned. The example-centric programming is definitely abandoned.
Go academia.
Yeah, I mean, that's how it is, right? Yeah. Like, we know Joel Brandt, and he's definitely not working on it anymore.
That's right.
Well, ours is, yeah. I mean, it depends on how, we're not the fastest people, right? But we're only 2 of us. I mean, it's open source, can help us, but yeah, it's in active development, yeah. Hmm? Yeah, so I mean, we are a startup, and the code is open source and online, and you can contribute to it. But yeah, it is a startup.
Which will be more helpful for you in the long term? More memory or more faster CPUs or both? Or?
So it doesn't. I don't think we'll be limited by either of those so much in the long run. So the main thing is that.
I mean, you're going to get more.
So sorry, I should say the question. So the question is, are we limited in the long run by CPUs or memory or
which will help more too?
Which will help more. So I think we're most limited by algorithms. So what we've currently done is very limited by CPUs and a bit by memory. But if you go a little further than that, and you sort of start to train these models from large amounts of data, then probably memory and latency are the bigger issues. So if you train a model on all of the code in the world, so that's obviously something you would do not on everyone's computer. So that would be a cloud thing. You're going to have more rapid sort of talking back and forth with servers. And you can either do it via latency, like either having the search sort of asking your server, but that's probably too much because it has to ask a lot of questions. So that's probably out. What you can do instead is you can modularize this model that you've trained on, sort of build a prior that say, here's the prior for Spring, and here's the prior for other Java libraries. And then you can, if the user starts their project and it appears to be using Spring because it's in their project, you can download that chunk of the model, and then you're down to memory. But again, I really don't think that it's a big memory hit. I think the only reason that we're memory troubled is that IntelliJ has chosen a low number for their default JVM size. And once you've launched IntelliJ, it's fixed at 750 megabytes. You can't grow.
They don't allow it to grow.
The Oracle JVM can't grow from inside. So it's a stupid reason, and we could fix that if we sort of had we do have instructions on the web page, like here's how you would increase your memory, but we can't make that we don't know how to make that an easy install process. So there's no real fundamental reason why we should be memory limited. It's just the current default settings of IntelliJ.
Having faster or more CPUs would help some?
So yeah, you can certainly parallelize this generally, and that speeds up. But typically the kinds of, so I've done for fun, I've done other sort of like combinatorial game programming, like say chess or things. And the speed that you get out of those, parallelizing those algorithms, which are sort of these deep search algorithms, is sublinear. So you throw 4 cores at it and it gets twice as fast. So because so much of the speed is pruning, which is similar to our domain. So we want to do a deep search, and then find a bound and use it to destroy another part of the tree. Whereas if you search both trees at the same time, you'll do the search and you do a whole bunch of work, and then you realize that this is the better one, where you could have skipped work. So because of that scaling, it's I think there are a lot of other algorithmic areas to focus on before thinking about
So
parallelism.
just getting better algorithms.
Just better algorithms and better machine learning models. Yeah.
I think we're out of questions, but thanks a lot. Appreciate
Yeah.
it. Thanks, guys.
Thank you.